Vitruvius is attributed to writing De Architectura, a book compiling with some of the greatest discoveries and inventions of the ancient world. The image is by Marcus Vitruvius as it references his most famous work entitled 10 Books on Architecture, and was written approximately 20 to 30 BC. It was one of the first texts in history to draw the connection between the architecture of the body and that of the building. Vitruvius believed that an architect should focus on three central themes when preparing a design for a building: strength, functionality, and beauty. This was the main theme of the work. De Architectura had illustrations that helped to clarify descriptions, particularly those of technical devices of such machines as a hodometer, which measured the distance by dropping balls onto them. If we look at a synopsis of the book, we see how he was able to basically engineer the engineering process. If we can even think of this book as a large compilation of an engineering design notebook, in that way it was revolutionary. Book 1 was essentially the prologue to the rest of the book. It talked about an ideal education, principles of division, architecture, and where best to build a temple. And it basically talked about how not everyone can call themselves an architect. So in Book 2, on the origins of building and various materials employed in their construction, such as bricks, sand, stone, and wood, and other various types of wall. So basically, it was just talking about how the wall is not necessarily a pile of material, but it will last indefinitely. Book 3 focuses on the mathematics and the correct proportions of columns and temples. So the quote is that the upper diameters of columns should be enlarged to compensate for the increasing distances for the glance of the eye as it looks up. Book 5 brought in the deities into architecture and engineering, and it basically talked about how to structure temples and stuff like that. Book 6 focused on the effect of climate on character and the best foundations for layouts for private homes. So it basically talked about how bedrooms and libraries should face east and libraries should not rot. Book 6 focused on paving, vaults, and wall paintings, including the best colors and their origins and the history of use. So it basically talked about purple and how it was the most outstandingly beautiful appearance of all the colors. Book 8 is concerned with water and aqueducts, and we saw a little bit about Archimedes' screw, and they talk about it in this chapter. Book 9 focuses on the study of astronomy and the relevance to architectures as a measurement of time using sundials and water clocks. But most importantly, this is where he documented Archimedes' finding of the density of gold. Looking at this Latin passage, we were able to translate what exactly he said about it. In the first paragraph, he talks about how some of the gold had been abstracted and how Archimedes was on the case to figure out whether it was fraud or not. Then goes through the engineering process, talking about how Archimedes measured and weighed each of the silver and gold samples. Book 10 finishes off by describing various machines and gadgets such as distance measuring devices, water-driven machines, and weapons like catapults, ballistae, and siege engines. Vitruvius thought that the successful architect and engineer should have both theoretical and practical knowledge based on broad and deep understanding of all the sciences. Let's get a little deeper into civil engineering, starting with the science behind arches. Let's take a look at the very visual reasoning behind using arches to support structures instead of a flat top, using unresolved free body diagrams. Before we look at why an arch would work, let's look at why a flat top would not work. Let's say I have 5 blocks right next to each other, which act as a continuous piece of material, and imagine it being broken down into an infinite number of segments. Now, if we zoom in on just one segment, there are 3 forces that matter that are acting on the segment: a force of gravity pulling down, and 2 forces from the neighboring segments pulling it up to keep it from falling. So we know that all the forces acting on this object need to be adding up to 0 in order to keep the arch stationary. Remember that I'm ignoring frictional forces, and if we stack these two together, we see that it's about the same size, and looking at this visually, we see that these two are equal in magnitude, these 3 forces. So what's the problem here? The critical issue, though, is where the forces act. Gravity pulls on every subpart equally, which has a net effect of acting on the center of mass of the segment. And the forces from the neighboring segments, though they're contrary forces, act where they come together parallel to the boundary. The end result is an upward force on both ends and a downward pull in the middle, which will tend to stretch the segment down. Now let's take a look at an arch. So let's say this arch is composed of infinite number of trapezoids, but I only have 3 in this picture, and we're going to take a look at this top one, because it's unique. Focusing on the keystone, we can see how this changes the dynamics. We still have a green arrow pointing down for gravity, and we still have red arrows parallel to the boundary But the change in shape means we also get a contact force perpendicular to the boundary on each side, pushing up left or up and right. So for these discrete blocks, this is Newton's third law of force. As gravity pulls the keystone down, it presses into the blocks, or either side, exerting a force on them, and they press back with an equal and opposite force. If we stack them together, we see that the x's and the y's add up to 0. And while we have the forces acting in different places, because they're directed inward, they don't stretch the blocks, but they compress it instead. This is great because stone bricks and concrete have tremendous strength and compression, so it maintains its integrity. Now let's look at one of the side pieces, and technically the dynamic of the side piece doesn't necessarily matter, like where we choose it from, because the resolved will always look the same. Here we still have gravity pulling down, but now the two contact forces have different magnitudes. On the upper side, there's a contact force from the second block up, which is due to both its weight and the push it feels from the keystone. On the bottom side, the force is much larger because it needs to match the vertical component of both gravity and the push from the rest of the arc. If we solve this all out, we notice that they don't add up to 0 perfectly. There needs to be a leftward-outward force, represented by the red arrow, and this is usually countered by something else, generally talking about a big wall of some sort, and this is basically pushing the arch together. The great thing about arches is that these are all compression forces, and when we're making an aqueduct, we can just change arches together to infinity, and the outward push of one will provide an inward push needed to hold up the next one, and vice versa. Now to the rest of the video. Roman roads were built in several stages. First, workers dug about 3 feet down into a terrain, then planted heavy, wide stones in set, and then covered with the dirt or gravel to allow for drainage. Engineers insisted of using straight lines for their roads and intended to push through obstacles instead of building around them. That required an enormous amount of manpower, but manpower was something that the ancient Romans always had in spades because of the slaves. Simple stone walls were the earliest type of Roman wall, and it was constructed by placing stones of various sizes upon one another without the use of any kind of binding agent to bind them together. This was a method called opus quadratum, described in De Architectura. Blocks of stone of the same height were set in parallel courses without mortar alternating. Sometimes they also used sun-dried mud brick, and it was kind of an adobe that was used throughout the world for thousands of years. It was durable in dry climates, but got soggy during the wet ones. With the concrete revolution, concrete was developed by experimenting with the type of mortared rubble construction called opus caementicum. It was made by adding volcanic dust to a mixture of brick or rock pieces, lime, and water. Romans started building walls made of concrete at a much faster pace than with constructions. Walls had an inner core, which consisted of an abundant mortar facing with stone and brick, which also had more walls that were pleasant to look at. During the 1st century CE, the use of opus testacum wall constructed technique, and it was a brick-faced concrete rather than tough or other stones. In the middle of the 1st century, most walls were predominantly faced with similar bricks, or a triangular shape. One reason for the development of brick facing was the development of the brick industry and the Great Fire of Rome. So this also leads to how they wood-fried bricks now. Fired clay bricks were made from clay. Clay had to be extracted from deposits, ground and mixed with water, and then shaped to form bricks. These bricks were then dried and fired at a chamber at temperatures around 1000 Celsius. Roman bricks were longer and of a lesser height than modern bricks, and it made the variety of shapes and sizes, with the longest bricks measuring over 90 centimeters. Roman legions, who stamped the bricks with their mark, also spreads Rome brickmarking know-how throughout the empire. And of course, there were also defensive walls. Rome had only a few walls defending its borders. Hadrian's Wall was built from 122 to 128 CE to protect the province of Britannia. It was constructed using only local materials, not concrete, which required large quantities of water, and not bricks, which could usually be produced with massive quantities. In conclusion, as construction techniques evolved, so did the methods to construct walls.